Okay, welcome to the last talk of this session. It's a great pleasure to welcome Philippe Faist here, who will tell us about some recent results that are relating uncertainty relations with quantum metrology. Please go ahead, Philippe.
Thanks a lot, David. Thanks a lot, everyone, for tuning in. It's a great pleasure to have this opportunity here to give this talk. Thanks a lot to the organizers for putting this effort into getting the the best possible QIP experience given the circumstances. Thanks for that great work. All right, it's really great to be able to present this project I've been working on recently with Mischa, Victor, Joe, Jens, and John from a bunch of different places. The main point I'd like to talk about today is how I want to consider quantum clocks and see what happens when they're exposed to noise. Most specifically, I want to understand how their sensitivity decreases once they've been exposed to some kind of noise channel. And the way we'll do that is by finding some kind of information trade-off between time and energy, between the noisy clock and the environments of the noise. So, this work? All right. So for me, a quantum clock will simply be just a pure state that evolves according to a Hamiltonian. I'm just going to think about a clock like that. So I have a Hamiltonian, I know what it is, I initialize my clock in a pure state. And if at a later time, I'm interested in knowing what time it is, well, I perform a measurement on this clock, and hopefully this measurement will give me some kind of information, will reveal some kind of information about how much time has elapsed since the moment that I've initialized this clock in its initial state. And of course, in practice, this would typically be in some quantum system, you could choose two energy levels, different energies, and prepare some kind of superposition of these two energies. In that case, this thing will pick up a phase over time, and this can serve as a clock in this sense. The main question I'll be addressing during this talk is, well, if I expose this thing to some noise, what will happen to its sensitivity? All right, there's already been a huge body of work that's been addressing this question. So I do want to mention at least a few things about what has been done before. There's been a large body of work addressing the question of how can we use quantum error correction to mitigate the effect of noise? Can we protect the clock state or the probe state if you're sensing some unknown parameter? Can you protect that against the noise by using a quantum error correcting code? And there's one of the main contributions of this body of work is really to see that you can actually recover the same sensitivity scaling as you would get without the noise if you use it by using quantum error correcting code, if your Hamiltonian, well, if and only if your Hamiltonian is somehow not in the linear space spanned by all the noise operators. Another possible approach, if you're interested in exposing clocks to a noise channel, one thing you could do is to ask, well, can we use some kind of quantum error correcting code before sending it through a noise channel? This is a bit of a different setup here. And that's a setting that was considered in this paper by Patrick Hayden and collaborators. And well, they noticed that they pointed out that if you want to do this, you need a time covariant error correcting code. And it's kind of annoying because in finite dimensions, you can't find such code. So I forgot to mention a time covariant code is a code where the logical time evolution can be implemented by time evolving each of the individual subsystems here in the encoded state. Now, in practice, what you'd probably want to do is look at something more like an approximate quantum covariant code, because there are in finite dimensions there are no such time covariant codes, for instance. And there's again a body of work that explores these settings and makes some interesting connections to metrology. So the setting that I'll be considering is a very simple one. We initialize our clock in some initial state at time 0. We let it evolve for some time. We have maybe at time t0, it's in a different pure state. And then we apply a noise channel onto this clock. And so we have a noisy version of this clock. And the question is, how much sensitivity is there left? All right, let me give you a brief outline of how I'm going to address this question and what I'll be telling you over the rest of this talk. First of all, I'll tell you about this uncertainty relation that I've been talking about, that I've been mentioning. And this uncertainty relation will relate the noisy clock sensitivity to time with the environment sensitivity to the energy of the clock. And that will in turn allow us to write down some kind of expression for the sensitivity loss of this clock due to the noise. Then there are some additions that we'll add on top of that. We can get kind of bounds on the sensitivity that could be interesting. And we can generalize this uncertainty relation for any two power parameters, not just time and energy. Then there's another, you can also ask the question, well, when is there zero sensitivity loss? Is there a situation where that happens, where all the sensitivity is preserved? And we'll connect that to the idea of quantum error correction and kind of a variant of quantum error correction that is relevant for this setting here. And I'll finish by going to an example of a many-body system, an Ising Hamiltonian, and subject that system to IID amplitude damping noise. All right, let's start from this uncertainty relation. And even I need to start by telling you what sensitivity even means for me. So, right, if we have a one-parameter family of states, I'm interested in local sensitivity. And what that means is that locally around some time t0, I'd like to find an observable. This observable t here on the slide, I want to find an observable such that the expectation value of this observable to first order around this value of the parameter t0 gives me the correct value of this parameter t0. So, so the expectation value really reveals the value of this parameter up to, if we ignore second order terms in variations of this parameter around t0. And in this context, a very important result is the Kramer-Rao bound, which tells you that the variance of this observable is necessarily lower bounded by what is called the inverse of what we call the Fischer information. And the Fischer information is a quantity that depends only on the state here at this point t0. So it depends on rho of t0 and on the derivative of the state locally at that point t0. For the purposes of this talk, I will define the Fischer information in this way as the optimal inverse variance of such an observable. So this inequality here can be achieved by some optimal observable t, which I'll be referring to as an optimal sensing observable. And I'll use that to define the Fischer information in this way. If you looked at this slide and thought, hey, maybe this is a semi-definite program, then congratulations, you're correct. This is an SDP, and I'd like to refer you to Hamza's tutorial on Saturday on semi-definite programming and applications in quantum information, which was very informative. One last thing I want to say here is that this T here that I've been mentioning as this sensing observable, the optimal T is, the condition for optimality is given by this thing. If you've heard about it, you might have heard about it already in the context of quantum metrology. It's the symmetric logarithmic derivative. And it's, we know that T is optimal when the anti-commutator of rho with T is proportional to the derivative of rho at that point T0. All right. I also want to mention that if you have pure states, everything is very simple actually to determine, and I'll come back to that in a minute. But if rho is mixed, sure, it's an SDP, but it can still be tricky to really get a good handle on what this Fischer information is and what this what shape this optimal sensing observable has if rho is a mixed state. All right, now in the context of our work, we consider a pure clock that's been initialized in some pure state. It evolves according to time, according to this Hamiltonian, and we're interested in local sensitivity around a point t0. Now, somehow I want to define what it means to be sensitive to energy, right? So what I'm going to do is, well, we have this observable T, that's a Hermitian operator. We can use it to generate another evolution. Let's just take the commutator of this observable with psi and define that to be the derivative with respect to a new parameter, which I called eta. Now, why on earth would I want to do this? It just kind of came out of the blue like this. But it turns out that if you look at an evolution in that direction, the optimal observable that you can use to sense the value of that new parameter is the Hamiltonian H itself. So this really gives us a complementary picture of two generators here. We have the evolution along that's been generated by the Hamiltonian. You sense it optimally with T around this point T0. And for the other evolution, it's generated by this T observable and it's optimally sensed by H. So you just swap the roles of T and H between the two evolutions. And the state here at this point, from now on, I'm really considering everything local around this point. So I'll just be writing this state here as psi. Now, a couple just expressions for these quantities as we move on for the next points of the talk. The derivative in the time direction is just the Schrödinger commutator with psi of H and psi. And the derivative in the eta direction is, I defined it to be this commutator. But if you plug in really what the optimal T is here for this case, you'll find that this derivative is actually proportional to the anti-commutator of the Hamiltonian with psi where I kind of shifted the Hamiltonian so to make sure so I've shifted it by a multiple of the identity to make sure that psi has 0 energy expectation value. So it's a convenience, really. And in this case, you can really work out what these Fischer informations are for both the time direction and the eta direction. They're just related to the standard deviation of the Hamiltonian at this point here, psi. All right, now we can come to our main result. We're looking at so Alice has this clock that's in the state psi that's been evolving maybe for some time t0. We apply some noise channel onto this. We get a noisy version of the clock. And we're interested in the sensitivity here after the noise channel has been applied. Well, we know that in quantum information theory, we can always look at what happens to the environment. And that's described by what's called the complementary channel. So we can look at what the environment gets by the complementary channel, and more precisely, we're going to look at what sensitivity the environment gets with respect to this complementary parameter eta. And our main result is really this: is that there's a trade-off between these two quantities. So Bob's Fischer information with respect to t trades off exactly with Eve's Fischer information with respect to this complementary parameter eta, and they both sum up to 1 if you kind of normalize them by the original sensitivities on the noiseless system. So really you have this trade-off, and these again these kind of f Alice t and f Alice eta, you can just see them as making the units consistent, because this is time, this is energy, and we have Fischer information 4 times, so like I guess inverse of time squared. But to make the units consistent, you kind of normalize these by their noiseless counterparts. All right, now we have this uncertainty relation. We can ask, well, how does this, how can we translate that into kind of, how can we investigate more precisely what's left for Bob, and can we quantify the sensitivity loss? So we can rewrite this expression just in this form here as f Alice t minus something, and that's something I'm calling this g, the sensitivity loss. And this g, you can see that it's just the Fischer information. If you kind of work out these constants that are in front of these of this f Eve eta, you'll see that it's the Fischer information of Eve's state with respect to a evolution whose derivative is given by this anti-commutator. So the image of this anti-commutator onto Eve's system. So this really means that you can compute the sensitivity of, you can compute the sensitivity loss at Bob's end simply by, subtracting this sensitivity, by simply computing this Fischer information here, which implies only objects on Eve's end, and subtracting that from the noiseless sensitivity. So, maybe that could be interesting if your noise is local, or if you have weak noise and you're in a many-body system. Maybe in such cases you can model your environment. Maybe you can model your noise as something that actually has a small environment. In that case, maybe it's simpler to compute the Fischer information on that environment. To give you an idea about the proof, I'm going to list the main few ingredients, and then the proof really follows by putting them together and going through the details, which I'll skip. So the first thing is that you can write, so I mentioned this, that the problem is an SDP. Now, this is actually the SDP that we're interested in, or actually, you can transform these pretty directly into SDPs. So the first thing that we're interested in is an expression of the Fischer information that is in terms of these variational problems, which are essentially SDPs. So that's the first thing that we work with. And the second ingredient that's necessary is we can rewrite, an alternative expression for the Fischer information is that it's actually related to the fidelity of quantum states. And specifically, it's the second order coefficient, if you like, if you expand the fidelity of quantum states between two neighboring points, rho of t0 and rho of t0 plus dt. If you look at the second order expansion of that, that's basically the Fischer information. So now you can put that together. You can look at what happens. So in our setting, you have a noise channel acting on a pure state. So you can take two neighboring pure states, see what their Fischer information with respect to so write down their fidelity, and use Ullmann's theorem to write that as maximization over unitaries on the environment, where we have the environment by the Steinspring dilation of this channel. And the key point here of our proof is to realize that this optimization over this unitary on the environment actually turns out to be the same as optimizing here over this S in some form of expression of a Fischer information for the environment side. So that's really just the parts you put together to get this proof. So let me give you an example here, just to fix maybe everything through an example. Let's just consider a single qubit. So a single qubit that has a Hamiltonian parallel to sigma z. They have the states that's a superposition of up and down. So it's it's pointing in the plus x direction. The energy variance of this state 4 times that is just omega squared. So omega being the coefficient here. If I let that evolve for some time t, I get a state that just has phases in the off diagonals, right? And now suppose that I expose this thing brutally to a partially dephasing channel where I damp the off diagonal terms by a coefficient 1 minus p. What happens there is you can work out what the complementary channel is. It's not too enlightening to do that, but you write down cross operators for this, and then you use the expression of the complementary channel in terms of the cross operators of the forward channel, and you get something like this. And this allows you to compute the Fischer information on Eve's end with respect to this different direction given by the anti-commutator, which corresponds to this energy parameter. So we can compute this sensitivity loss in this way. Remember, it's this expression here, this Fischer information here. This object here is the Eve state, and if you just plug in here, you'll realize it's just a diagonal state. This expression here, the second argument of the Fischer information, you can just again plug through here the anti-commutator, which by itself is just sigma z. You can plug this in, and you can compute this Fischer information fairly easily. It's the Fischer information is actually easy to compute if rho is diagonal. That's a thing I forgot to mention. And you get this expression here, so omega squared times 1 minus p squared. And you can check that if you compute Bob's Fischer information directly, you get omega squared times 1 minus p squared. And well, you can check that the difference between these two quantities is actually indeed the noiseless sensitivity for sigma h squared. All right, so this is kind of an example you can keep in mind where really the sensitivity, Bob's sensitivity to time after the application of this partial dephasing channel really trades off with how much Eve gets to know about the energy of this qubit. All right, so I talked to you about this uncertainty relation and the expression for sensitivity loss. Let me get to these kind of additional kind of extensions of our result. One thing you can do is in our setting, you could say, well, let's take Eve's systems and just apply an additional channel onto that. And what you might want to have in mind here is maybe I just apply a completely dephasing channel. Anything that can make computing the Fischer information easier. Like I told you, computing the Fischer information for diagonal, if your state is diagonal, is easier. Well, let's just kind of apply a channel that kills all the off diagonals. What happens there is you can just use the data processing information, the data processing inequality for the Fischer information to immediately see that this Fischer information has to be lower than this one. I can only decrease the sensitivity. I can only get a worse sensitivity afterwards. So this directly translates into an inequality for Bob's Fischer information. So we get an upper bound on Bob's Fischer information in this way. And I forgot to mention this, in this case, for instance, we're going to be using, I'm going to come back to this for amplitude damping noise in a little bit. The other possible extension of our main result is, well, what about not just time and energy? What if we're interested in a bunch of other parameters? And well, the answer is you can pick any 2 parameters that you like, right? You can pick 2 parameters, t and z. Say they're generated by observables or Hermitian operators h and z. What you get is that you get this inequality right here, which is again a Fischer information trade-off, but which is now valid for any 2 parameters. And kind of the constant on the right-hand side is simply that it depends really just on this commutator of the 2 generators. And one thing to note is that this second term here is equal to 0 if the 2 generators saturate the standard Robertson-Weil uncertainty relation, which you probably have seen in an introductory quantum mechanics course, which is this one right here. And that's the case, for instance, in the setting of our main result that I presented earlier. So this H and T generators do saturate this inequality here, and we recover kind of this 1 on the right-hand side for the energy and time parameters. All right, now let me move on to the connection with quantum error correction. You can ask, when is there no sensitivity loss at all? When is Eve's Fischer information equal to 0? Well, in that case, you can show that it's equal to 0 if and only if this condition right here holds. So EK are just the cross operators of the noise channel. And here I've defined some kind of virtual qubit subspace of my whole Hilbert space, which I've defined by identifying my clock state psi as the plus state of this kind of virtual qubit. And h bar times psi, I've identified that as the minus state up to a constant. You can check that they're orthogonal. And this defines a kind of virtual qubit. In there, I have a logical Z operator, and I have a projector onto this subspace. And so, you know, I have this condition here that tells me exactly when I have zero sensitivity loss. And you can see that it really resembles a lot the Knill-Laflamme conditions for quantum error correction. And if I had just this P, EK prime dagger, EK pi, EK prime dagger, EK pi, this thing is the expression that comes into the Knill-Laflamme conditions, but now we look at the projection on the logical Z operator of this thing. So in this sense, it's actually weaker than the Knill-Laflamme conditions. And this condition is actually closely related to the Hamiltonian Naughton-Lindblad span conditions that I've mentioned earlier. And also it's connected to the quantum error correction for algebras. All right, so just as a quick example of what you could do with this type of error correcting conditions, imagine I have a graph. Imagine I have a bunch of particles, and suppose that they interact according to a given graph. So I place a particle on each vertex of this graph, and I have a ZZ interaction for each possible edge of this graph. Now, I can ask, well, what is a good probe state for this Hamiltonian? What is a good clock state, sorry, for this Hamiltonian? You could think, well, let's look at just the one superposition of the least energetic eigenstate and the most energetic eigenstate. So that would be a superposition of an all zero states, for instance, and a configuration that violates as many of these interaction terms as possible. And you can check that these conditions actually are not satisfied in this case. On the other hand, if I include in the superposition also the all one states and the kind of flipped configuration, so it's, you know, again, the same two states, same two basis states, but now I also include their flipped versions. Well, now suddenly I do satisfy these Knill-Laflamme-like conditions. And we know that there's no sensitivity loss if I take a single particle and, you know, if I erase a single particle in this setup. So I've covered most of the things. And now let me turn to the example that I want to use to illustrate these concepts. So imagine that I have a 1D spin chain with an Ising Hamiltonian. So it's just a ZZ interaction on neighboring sites. Suppose now that I expose this system, this entire system, to to amplitude damping, but on-site amplitude damping. So an IID channel consisting of amplitude damping channels of each of parameter P. Now, if I look at this state I presented on the previous slide, just a all zero state, a superposition of the all zero state and the alternating 0, 1, 0, 1 state, you can compute the Fischer information, and it drops like this as a function of the amplitude damping parameter P. But if I look at the other states that I mentioned just before, like I look at not only the superposition of the 0, 0 and the alternating state, but also their flipped versions, you know, the all one and the other alternating state. Well, it turns out that, well, you can see that I've got an increase of sensitivity here. I have better sensitivity for low values of P. And I'm using this example also to showcase the bound that I mentioned earlier. Remember that I said that you can bound the Fischer information by further processing Eve's system. And in this case, you can decohere Eve's system and cut off and kind of forget high weight errors. And so that makes computing the Fischer information easier. And this is the upper bound that you get, this solid line. And you can compare that to the true value, which is this dotted line, and it shows that actually this upper bound is very good for these low values of P here. Now, if we focus, and this is again also the corresponding clock state. Now, if we focus on these low values of P, then we can see that we can kind of again compute for a larger number of qubits, and we can see that our bound is, you know, we can still compute it, and we still have kind of good results. So yeah, and one observation I wanted to make is that we can see that kind of this sensitivity loss only kicks into second order in P here, and that seems to be an interesting feature of some of these metrological codes, as we've been tentatively calling them. All right, now I've covered most of the things, so let me move to my kind of discussion and remarks. Basically, the main point that we're trying to get out of this is that if you want a better clock state, well then better use clocks that have better use a state that hides as best as possible its energy from the environment. The other thing I wanted to mention is that, everything I've said really holds for a fixed psi. So, it's more in the spirit of, let's find the guiding principle for how to look for good probe states. And maybe, restrict to probe states that are, or clock states that are easy to prepare in some setup. But of course, we'd be interested also in seeing if we can actually optimize in a systematic manner to find the best probe states in a given setup. I also want to mention that we redid a certain number of these proofs in infinite dimensions, and they carry through. So these uncertainty relations are actually still valid in infinite dimensions. And I've been mentioning clock states, but of course you can use these too for whatever kind of Fischer information expressions in this setup. So it could also be used for sensing an unknown parameter in the Hamiltonian. Now, oops, sorry. And I also wanted to mention that, I know this setup is a bit unconventional. You have a unitary evolution decoupled from the noise, and that might not be realistic. But if you make some additional assumptions and you kind of, in some settings, you can actually connect the two. And basically it boils down to can you kind of decouple the two evolutions in a way that's not too that doesn't incur a large error. All right, so now there are a certain number of other points, like information trade-offs are always interesting in quantum information theory because they tell you something about the structure of quantum mechanics and of quantum information theory. And you can see our Fischer information, our uncertainty relation as a Fischer information counterpart to a family of uncertainty relations that have been developed in the case of entropy measures. And okay, I see I'm kind of maybe running a little short on time, so I'll kind of skip through these points. So I think our results might be interesting in the setting where you're interested in these this more intermediate regime where you have maybe a weak noise, but where you're not necessarily interested in catching the Heisenberg limits in the limit of large n, but maybe you're before this limit actually kicks in. And I want also to mention that Fischer information bounds in general are often kind of not can often be hard to obtain for the general quantity Fischer information for mixed states. And so I think that's a contribution also that could be interesting. And also many-body metrology using many-body systems is something that has a lot of attention recently because there's a lot of promise for using them for sensing, for achieving better sensitivities in quantum metrology, such as for NV centers or for lattice atomic clocks. And well, we have some open questions that we find could be interesting to address, like can we find applications to cryptography, like for these entropic uncertainty relations? What can happen when you look at multi-parameter metrology? Can we still say something? And can we understand the sensitivity loss of these kind of metrological codes if we have, for instance, weak IID noise or anything that kind of goes beyond the natural distance of these codes? So with that, thanks for your attention.
Perfect. Thanks a lot, Philippe, for this very interesting talk. So Marius Junge has two interesting questions. Okay. First, he's answering how important is that you consider the Fischer information. Would, for example, entropy production also work? And second, does your advantage of metrological states come from some group representation? Sorry.
Very interesting question. First of all, let me address the first question. So this, let me go back to my proof sketch. So is it important to use the Fischer information? In the way we're doing it currently, yes. We really use this variational characterization of the Fischer information. So if you want to use a different quantity, then we probably have to work to kind of see if the same type of argument can be extended to that case. And it's not obvious how. I mean, of course, the fidelity is related to, for instance, the Renes 1/2 entropy or stuff like that. So I could imagine similar expressions working also for entropies. But again, in that context, there have been a lot of entropic uncertainty relations already explored. So maybe we want to check what's been done there more precisely too. But the short answer is our proof is really for the Fischer information and it doesn't immediately apply to other quantities. And sorry, the second question was?
The second one was whether does your advantage of metrological states come from some group representation?
I think yes, in a certain sense, yeah. One way of seeing, like one family of codes, like of these codes, is is, for instance, so what, yeah, you can do it that way. It's not necessary, but you can. So you can find, for instance, time covariant codes. If you have a covariant code, then automatically it satisfies these conditions here, right? So in that sense, if if you have a code that commutes, you know, for which the encoding commutes with this time evolution, then that gives you a code that satisfies these conditions. But what's interesting is that you can, it seems that there are, you know, because these conditions are weaker than the full Knill-Laflamme conditions, it seems like you can have systems that aren't themselves proper quantum error correcting codes in the complete sense of, you know, satisfying the full Knill-Laflamme conditions, but that still offer no sensitivity loss. And there might be some group covariance argument there, but I actually don't know. I'd love to chat more about that.
Sure, yes. Okay, again, as usually, there are many more interesting questions that we don't have time, but maybe Philippe, if you have some time, you can maybe later check them out on the Slack channel. Thanks a lot again for the talk. And I would like to remind everybody that now the roundtable discussion starts. So if I understood it correctly, everybody that is interested should just now move to a roundtable discussion and we can continue the discussion there. So thanks a lot for joining and have a good afternoon, morning, or evening, wherever you are.
Thanks a lot, David.